important. What I will say is a bit of a drag is when I'm typically at these things, I'm usually getting really hammered by, and I don't mean, with by imbibing anything rather, but by my good colleagues, JJ and Scott. And then I only had to look over to my phone and saw that JJ was giving it to me. So this is good. So I feel very comfortable now. Yeah, we've got a real who's who of difference makers in wind energy research here. So this is a real flattering thing to be a part of. And so I'm super excited for our session today. I was going over the slides and wow, I can't believe the work that's being done in this space. And credit to WeCan and NRCan for putting this together, because it was really good to sort of shake the bushes and see who was doing what, because it's really easy to work in isolation on a lot of these topics because the topics are so huge, and it's very difficult to stay on top of who's doing what and where. And so this network attempt, I think, is an honorable one, and I think it's going to be very good for Canadian wind energy research. So this is a wonderful thing. So I just want to offer, this is sort of the introduction part, and like I said, I think we'll probably move rather swiftly today. I'm speculating because well, some of the talks belong to our group, and they're quite related. And so to avoid too much redundancy, I suspect I'll be concise. And then maybe we will be able to capture some value at the end with the extra time with discussion from others. And so, but I want to just offer this about, and this is titled asset management, right? And I thought about that. Usually I call this stuff life extension, and that's because that's my prime purpose on this planet, is to see if I can make it to like 150. I'm a neurotic person by nature, and I worry about my own mortality all the time, and which made me a real natural for trying to figure out the mortality of the wind turbines. I worried along with them, but I'm thinking about it now, and asset management, and again, we know asset management is extends to everywhere in the business world. So for that reason, it's a good term. But it's also a good term because it's not always about extending life, because we've all seen life extension where maybe it wasn't the best, it wasn't the best outcome, right? Extending a life should be a good one. And you want that for your wind farm too, right? And that's, to me, that's what asset management is. Asset management is getting the most out of your assets that you can every moment of every day. And that goes for hopefully your own personal lives, but also for your wind farm. And that's exciting. And in my mind, that makes this topic the most important of all of them, because it's all encompassing. And, I had this conversation with Ryan at NRCan when we were rallying for, support for Task 42, which looks at asset management and life extension. And I said, listen, like, I think this topic really represents so many things. It represents operating today. It represents how we operated in the past, and it frames the next generation of wind as well. And and in looking through some of the slides that we're going to be seeing today, I can certainly see that others share that approach. And so I'm really keen to learn more about sort of what we're going to be getting from our great colleagues here. And when you look at asset management in wind, it's a little trickier than it's been for maybe other industries, because it is relatively new, right? The megawatt class of wind turbines, we're largely in the first generation of the commercial megawatt class of wind turbines, and it's starting to wind down, right? We've got some farms that have aged out past the fabled 20 to 25 years in Europe and in North America, but not a significant sample size. So we're still really in the dark about what's going to happen as we move from that first, in many cases, power purchase agreement to the second one. So it's tough, and it's a spectacular thing as well when you consider it's a huge structure, right? These turbines are huge structures, but they're also huge machines. So much complexity, right? So much complexity, and the other thing is that they're all different. They're all different. Every single machine is different. So the blade specs from the factory can have some variance on them. And in the end, that'll be washed out by the differences in the foundation conditions at your site from one place to another. So you might have a Siemens 2.3 megawatt Mark II on one location, and you move it to another location and you don't have blue clay anymore. You've got something that's loamy. So now all the frequencies of response are different. So there's all kinds of things that we have to consider when we're trying to do things that tempt us, like archetyping. Archetyping is great because you can speed things up, you can start to make rules, you can start to, sort of shape expectations for people, but they're dangerous too. And so we have to bear that in mind as well, right? So that's sort of my introduction. And if we could, if we could, controller, could we move to the next slide? So, as I said, being a neurotic person, worried about mortality, around 2015, this started peaking for me. And so I got together with some like-minded, far less neurotic and more productive colleagues at the University of Windsor and Western Ontario. And so my good colleagues and friends, Lindsay Miller, Matt Davison, who I see are here today, and David Ting and Han Ping Hong and Tim Newson, we got together and started talking about what happens as you reach the fabled year 20 and you move into year 21. What are the considerations that a wind farm needs to make? And so we worked hard and put our heads together, and we put another number of funding applications together, and we were fortunate enough to get support from three tremendously visionary companies in Kruger Energy and WeCan and Enbridge. And so that industrial money was very useful as it seeded money from NSERC and from, at the time, it was called OCE. And we had enough funding to get a number of students working on some really interesting topics. And year 21 really was, for us, the birthplace of sort of our play in asset management. And it started with this diagram, and I would update this diagram now if I didn't have such a nostalgic appreciation for it. But really, this is what year 21 was about, was that we were really trying to understand that in the end, asset management is about understanding the value of your assets to the minute. If you can do it, that's the very best you're going to be able to do. And that involves so many things. That involves understanding what the market has for value of your asset, for your service. That's understanding how much life is left in your asset. And to do all those things, to understand value, you need to understand all the costs, and you need to understand the revenue generation opportunities that you have to do that. And that's what we tried to do in our study. Was we tried to start with our investment valuation model. And despite getting kicked in the ribs and punched in the kidneys by people like JJ, about, hey, we really want to know when things are going to break. This is what's more useful to me. I need to understand when we're going to change things out. I thought that's what we're going to be doing. And he was right. We had to do that as well, because that's a huge piece of your economic puzzle, is when do things need to be changed, and when do we need to proactively work to have spares on site, etc. But there's all those other bubbles too, right? There's, can we get our product to market if we're being more generic than just our specific case studies? What do our taxes look like? Are we going to be able to get our land lease again? Do we have environmental concerns? Has a new species of bat moved in that has basically shut down our operation? So there's a number of bubbles to consider when you're doing an investment valuation model for a wind farm. And of course, some bubbles are easier to fill in than others, right? It's really nice. Things like the cost of capital. Well, if you're lucky enough to pick up that figure from somewhere, that can be filled in pretty quickly. The landowner agreements, maybe you're really lucky. Maybe you've got some simple landowner agreements, right? Maybe your social license was done really well. And we were really lucky because the companies that we worked with were kind of real sort of trendsetters in the social license development category. So that was really easy for us. But then you get into things like maintenance, right? And that's a massive one. And you uncork that bubble and you look inside, and there's all kinds of things in there where we have to understand how long will the drivetrain last? Other things were pointed out to us by our colleagues, like, how long will the converters, the inverters last inside the machine? What about the computers, right? And you've got all these different tools that you can use, and some of that was already available. That was the exciting thing about it, is the literature is full of remaining useful life estimation techniques for all types of different components. But of course, they're not always perfectly applicable to your application. And so that's where you have to start to understand what they really mean. And then you also have to get the ever so vaunted data, right? The data. And, this is where I say that any work that's as complex as this, and I see the slides that we have coming up, and I see the stuff people are delving into, it's really amazing. But it's really about relationships between variables, right? And these variables, you need to appreciate, will go through different values that I'm going to roll to my next slide, please, because it rolls right in. So these variables that you have, ultimately, you need to understand the relationship between them. And then you need to understand the relationship between the people that manage those variables as well. So it's great to have data. And, you guys know, you've been in this work for a while. You ask for the data and they'll say, what do you need? And you say, oh, give me everything you've got. And they're like, no, what do you need? Because there's just too much. It's unmanageable to ask an owner or an operator to give you everything. There's no everything. You can shut an operation down that way. So you really need to know what you're looking for. And that has to be a decision that you arrive at with not only the people that will analyze the data, but the people that understand the data, even in its raw form. And I can't emphasize that enough, is that is really important. People talk about analytics. They really need to, what they need to say is it's about informed analytics. Analytics that are informed by experts who control the devices that generate the data, so that when you see outliers, you can take it to an operator or you can take it to a technician and say, do you have any idea why this did this? And they can say, yeah, this machine was down for 3 days, or we put a new blade coating on that, or we had to curtail during this period, right? And meanwhile, you could be spinning your wheels on anomalous, features like that for days. So ultimately, the work we did in year 21 migrated to our participation in Task 42 for the International Energy Agency. And when you look at this, could I have a click on that slide, please? You consider all the variables that are in play, and we've talked about a lot of them already. You want to seek out the ones that are most influential, because if you can tabulate every single one of them and understand every single one of them, fantastic. But in the end, our resources are always limited. So you want to find the influential ones. So you're really trying to understand what is, the structural life remaining, and what are the remaining useful life of the load carrying and non-load carrying components, matched up with the features of our compensation agreement. Because, you can mess around with details on, leading edge erosion for blades. And I'm not trying to trivialize that. That's a really important piece of operations, right? But if your PPA is so rich going forward that you can actually afford to replace every blade on the farm, then, let's not waste too much time. So you've got to keep everything in the context of the lens of the power purchase agreement, right? And then if you find out that your PPA is so tight that you have to pinch every penny and you have to pinch every leading edge, then so be it. But that's the really important piece, is that you have to really, can I have another click on that slide, please? You have to really understand that, identifying what's going to really control your day at the end. And for us, it was really about really understanding PPAs, really understanding the physical modeling, if we could, that ultimately adds up to farm value. If I could have my next slide, please. So we also, after working in Task 42, we were sort of recruited by the folks in Task 43 because of our work in life extension and repowering. There's a work pack in that task that looks at digitalization. So Task 43 is all about digitalization of wind farms. And this work pack is on the digitalization sort of intersection with life extension, which I was really excited to be a part of. And Lindsay and I have been working on this since this was a technical meeting, I guess, in Boulder. And the exciting piece here for me is that ultimately, you know, what this task represents is that properly digitized data streams can really unlock true asset management to the second. And that's tricky, right? Like, you know, for different farms, depending on the farms you visit, you want to pick up maintenance records. Sometimes they were sketched. If you're lucky, they were sketched on a piece of paper, or you know, if you're really lucky, they're in a spreadsheet or in digital form. But in any case, their formats may not be the same. And in a perfect digital world, you're talking about templates that are universally adapted across a platform, maybe across a nation. Can you imagine that? And all the data goes into the right baskets. And so all the algorithms that everybody's agreed on, or maybe there's a few that we're evaluating, but they all come from the same data baskets. And so, you know, if you can do that, then you can do some of the things that, you know, we attempted here. We had some really neat work done on principal component analysis of the behavior of blades. You know, we were monitoring how blades behaved over time, and we were able to actually isolate when blades became damaged, looking at hindcasting, looking at historical data, what happened when the blades were repaired, they returned back to the sort of normal state. Even things like just really basic stuff. If it's digitally available, you can look at how certain machines are performing across the farm. You can rank machines based on their performance. You know, how many spins are they getting? How often are they pitching? Who's making the most power and why? You know, these are super basic questions, and SCADA systems should do that, and many of them do, but some of them still don't. And that kind of stuff really gets you in touch with asking more questions, right? And that, we saw that was useful, particularly with this collaboration. We had some fantastic experts at WeCan and at Kruger, and we had good support from Enbridge in terms of data availability, but WeCan and Kruger were really invested in this project, and they really educated sort of our process for us, and that sort of put us to where we were, and where we're at a point now where with Task 43, working with Ryan from NRCan, we're really figuring out what needs and what the digitalization really needs to look like to streamline this process of asset management that is so critical for our next generation of wind energy, and really getting the most out of the investment for our wind farm owners. And when we say that really is just about, it's thousands of people. You consider the people and the companies that are invested in wind, and our collective future, if we're really interested in a properly clean planet. Clearly speaking to the converted here, but wind is a beacon for that. And so with that, I will relinquish my long-winded, if you will, chit chat here and pass to our next presenter. So thank you.
Okay, can you hear me?
Yes, we hear you, Claudio.
Oh, thank you. Thank you. Interesting presentation. I guess is a good lead to what I'm going to be talking about. I'm a professor at University of Waterloo, and this work I'm going to be discussing very briefly was carried out under an NSERC engaged with the Blue Wave AI at Ottawa. So it's basically about, as you can see, prediction of failures in a wind farm. So the main objective was actually to using data that Blue Wave acquired was given to basically develop techniques to using multiple machine learning techniques or models to detect failures. Okay, so we got a big database, and then we were trying to predict 1 hour ahead on time based on historical data whether you have a failure. So it was 1 or 0. So failures or no failure. We use several techniques, AI techniques, machine learning techniques, artificial neural networks, long short-term memory, networks, support vector machines, and ensemble learning, which AdaBoost, adaptive boosting, is one of them, but specifically we focus on adaptive boosting. And then using data from a site in Prince Edward Island in Summerside, we data from 1 year, basically August to 2017 to 18, we basically detect, or were able to develop some techniques to detect these failures. Before we did that, we used partial autocorrelation function to basically reduce the number of features of the data set, so make it more manageable. And then we did several analyses. All of this is described in these thesis that you see here. We're writing a paper, or we're basically submitting a paper on this soon for a conference. And basically the best results we got was from AdaBoost, not only in terms of prediction, which was somewhat similar to the other techniques, but also in terms of implementation and tooling, which it can be a challenge when you're using machine learning techniques, the type of parameters you need, how to evaluate them, etc. And then we use these are the results that are presented in front of you, are the results that we obtain. And we use different indices, if you will, to evaluate the performance of these techniques. And in this particular case, the one we have in front of you is AdaBoost. And we basically were able to determine that with the historical data we had, based on training sets and validation sets, etc., and testing sets, that basically 1% of the basically 1% of the time we miss the failure. So was pretty good at predicting, non-failures. And about 83% of the time we were able to predict the failure. So it is not perfect like any other machine learning technique, but was reasonable. The results were reasonable, and we believe that could be useful for this particular site to predict failures in their system. Okay, that's all I had. If you want to have more information, you got to get more information, more details. Please click on that. I believe that this will be available to you at some point. Anyway, click on the link and tell you to the thesis, which is, you should be able to have access to it and get all the details of it. Okay, that's all I have. Rob.
Fantastic. Thank you, Claudio. That's
Sure.
great. Yeah, so I think we will definitely, I'm sketching down a couple little points here. We'll have a discussion at the end. So thank you very much.
Sure.
So I will, Chris Mashevsky is a professor at Queen's in mechanical and materials engineering. Chris had to dash, so I'm going to cover his slide for him. He's got a number of interesting projects going on here where he's got data-driven, physics-based, and digital twin condition monitoring approaches going on. So he points out that a lot of industrial applications lack sufficient data for trustworthy data-driven fault detection. And yeah, we've all seen that, let alone fault classification and RUL estimation. So he said hybrid models can be used to generate synthetic data to augment training or provide system-level insights into expected performance and significantly improve model representations. So he's got, and I really like those statements he made. That's interesting. So he's got 4 different projects here. He's got bearing conditioning monitoring and wear prediction, where he's using a hybrid statistics-based data-driven model. He uses a statistical model with historical data to enhance RUL estimation, or sort of traditional machine learning algorithms. He's got gas turbine blade profile degradation prediction, hybrid physics-based data-driven model, able to distinguish between and predict progression over seasonal turbine wash requirements, and overall RUL estimation, degradation over 3 to 4 months versus over 3 to 4 years. So that's quite telling. Gear wear detection and prediction, hybrid physics-based data-driven model, physics-based model of gear mesh stiffness, where they generate synthetic data to augment measured vibration data for training of AI for fault classification and RUL estimation. And finally, tool wear detection and prediction for hybrid empirical measurement data-driven models. So empirical measurements of real tool wear during controlled experiment, where they used augmented training of adaptive narrow fuzzy interface systems based on cutting force measurements. So they collaborate with different industrial partners, academic colleagues, and the lab at NRC. They have access to a pool of exceptional research scholars. So a little sales pitch there for potential future employees. So yeah, good for Chris. So that's great. We will have Chris's obviously information now, and we've got his contact where we can reach out to him if you have interest in his work. So that said, I say we move on, controller. Robbie, exciting. We've got our weekend person here to talk shop. So Robbie is the data quality coordinator at the Wind Energy Institute of Canada. And this guy really gets into the details. I'm excited to see this. Take it away, Robbie.
Hi, can everybody hear me?
Yes.
Okay. So what I'm talking today in this brief 5-minute slide is some of the data that we're pulling in now for our turbines versus what we were originally. So the turbines we have are the DeWin 9.2 2 megawatt turbines. And initially, the OEM SCADA system provided us 60 10-minute averages with mins, maxes, and standard deviations, but no digital states. So we didn't know how often pumps actuated, how often anything with circuit breakers would go or so on. And in this 10 minutes of data, we didn't have access to all the sensors that were available in the turbine, just the ones that they chose to give us. Around a fault of the turbine, we would get higher resolution data, 1 hertz and sub-hertz data for 10 minutes or less around the fault time, but no relevant historical data to go off of. So if you're trying to figure out, was your turbine behaving the way that it was before, it's very difficult to figure out if that's indicative of normal operation or how it was just leading up to the fault. And another aspect of the turbines is there was no easy remote accessing of the data, that it wasn't sent to you or anything that you could easily monitor. You had to remotely log into the turbine through their software, log into it and check its operating state. So those turbines were commissioned in 2013. And then in 2016, we installed an OSI soft PI system, which is basically a central data historian that offers more capability than just a simple database. So incorporating this in, we were able to use different integrators to pull data from our systems all into one central hub. And essentially, we went from these 60 analog data points to basically 246 analog values and another 294 digital states coming in at 1 hertz data. So we went from very decent data, you'd say, for a wind farm, to an immense amount of data per turbine. And that's kind of where I ended up coming in as this data quality coordinator. Is we're now pulling in an immense amount of 1 hertz data into this one central source. And it's kind of that organization and keeping it all organized and using it for this operation and aiding in the research. So I put some examples down on the bottom of what we're using this data for. And one of the things we're able to bring in is the statuses of the turbines are used to trigger notifications that are sent to our operations staff through text or email. So we're able to bring that in so that when a turbine goes down, the operations staff knows fairly instantly that it went down and what the cause was and can act accordingly. The other aspect bringing in is the OSI Soft PI system has a web-based visual component. And that's basically the next two pictures that are shown on the bottom. The middle one shows an instance where we had 2 sensors that were giving values that are set point and the actual value. And in the bottom, there's a green line, and that green line was another input into the same piece of equipment that was reading 0, due to a broken wire. The first two, the orange line and the blue line, go into the OEM SCADA system, and we're showing the values that they should be. But the actual piece of equipment that controls the turbine wasn't getting that input, and that was missed in the SCADA system that we're able to pull out with this new barrage of data coming in. So for us, that was something we were able to basically troubleshoot on the ground and have the technicians aware of what the difficulty was and what they would need to do to fix it before they got to the turbines. So for us, that was a real good demonstration of what this new data could do for us versus what our OEM capability was before. So then the next part of the operation is bringing all this in. We're able to develop dashboards to give us real-time data from our turbines, showing all the various sensors coming in. And that's come a long way to not only our operations staff, but our researchers for looking into how these components work and how our turbines work in correlation to all these sensors interacting with each other. So that's been basically the last few years has been pulling a lot of this data and getting that better understanding. And we're now at the point that we can access this data by code and start using it for additional analysis. So bringing into machine learning, sharing with other research groups, our own initial projects we're going into, looking at icing and so on. So it's basically, while it's an insane amount of information, we're able to start bringing that context to it and sharing it with others. So how am I doing for time? I think I'm done. Thank you.
Thanks, Robbie. That's fantastic. This is great. So now we have a presentation from Nurjica. Whenever you're ready.
Yeah, hi, Roop. Thanks, Robbie, for the nice presentation. Hi, everyone. As mentioned before, it's an honor to be here today with you guys. And so I'm glad to share what we've identified at Nurjica as strategic research coming up, as Roop mentioned in the intro, that several wind farms in Canada will reach the end of their initial PPA. In 2026, at least in Quebec, we'll have at least one wind farm per year reaching that end. There have also been some signals from the government of Quebec, at least, to issue a call for proposal for wind, which would define the basis price that should be targeted for extended life of wind farms in Quebec. So that's an interesting, I think, context coming up in the next year. And so at Nurjica, we're having like the kind of a weekend, the two hats where we're both researcher but also asset managers. And so we own our wind farm. We have two Senvion NM92s. They're about halfway through their PPA. So commissioned in 2010 and ending up in 2030. And so in the whole context of the end of life, there's a few questions to be resolved. So what price could be offered in an extension of a wind farm of 5 to 10 years? How much remaining life is there in key components, specifically the blades, drivetrain, towers, and foundations? And then what business model is chosen after the end of the PPA? So is it life extension, partial or full repowering, dismantling? And so one of the way we decided to tackle these questions and I guess provide support to the industry is by installing a load measurement system as per the IEC-13 standard measurement of mechanical loads. So the installation of that system is planned for August 2021. It's been pushed away by COVID, unfortunately, we have a team of installers coming in from the US. So hopefully when COVID restrictions at the border are lifted, we can avoid that $40,000 quarantine period, which we're trying to steer away from. We have started a first project with André, I believe, who is on the call at Université Laval, and one student at ETS. So it's a one master's student working on a project about the impact of icing on remaining life in blades. And of course, what we want to do with this data is that it can be made available for academic or industrial research projects. And what that data is, so if you look into the standard, it's pretty straightforward, you know, what needs to be installed to be compliant with that standard. But basically, it's instrumentation in all 3 blades. So each blade would have, if you're familiar with, I guess, mechanical load measurement, would be 2 full bridges of strain gauge per blade, one at the blade root and one at about 1/3 wingspan. So that's about 13 meters into the blade. Then there's a full bridge on main shaft to measure torque. Then we would get rotor position, accelerometers in the nacelle, and then 2 full bridges, one at the tower top, one at the tower base. So the idea with that is we can derive extreme loads in all the main components, basically. So that's the general idea. On top of that, we have the pi historian, as Robbie just mentioned. So 1 Earth's data collected from the turbine, also from a neighboring met mass that we have in the back there. So we have anemometers covering the whole span of the rotor. So yeah, I guess that's the presentation, and I would like to thank the support from NSERC and the Quebec government on this project. But our aim is to have that this instrumentation brings value to research or the industry over the next 5 years. So if you have interest or questions, I can gladly answer.
Thanks, Charles. Fantastic slide and really interesting material. Yeah, I'll have some questions for you after. Okay, so we are now going to be looking at some slides from our friends at the University of Calgary. Kiao Sun is leading this study, building a wind turbine system model to assist health condition monitoring and failure prediction. Next slide, please. So Kiao couldn't be with us, and so I'm going to work through these slides for him. So their objectives are fault detection and diagnosis, including location and severity, remaining useful life estimation, and system failure prediction. So it's a model-based setup. Next slide, please. So ultimately, their capability, they hope, is to develop fault diagnostics and the remaining useful life estimation. They've got physics-informed feature extraction. So we have some familiarity with that, and that is an important piece of finding. I can just comment on this because of similarities in our work. Finding the right features to look at to determine whether or not you have a failure is really important. They also have physics-guided machine learning and system failure prediction. Next slide, please. So detecting new dynamics, that's an interesting piece that we've also, I would say, have really had an interest in. And it's exciting because if you're able to sort of pick up something new happening, new generally isn't good when you're looking at reliability, but it can be depending on what's happening. And so, and again, without being really familiar with his modeling details, I will say that they're also trying to pay attention to their uncertainty quantification. Next slide, please. So modeling the effects of different types of faults on the vibrations of a wind turbine drivetrain. So this is something that a lot of people are working on, and there's lots of room for more work on it because it's challenging. So, oh, wait a second. Is this Ali's slide? Is Ali here?
Yeah.
Ali, do you want to speak to this, Ali? Sorry, I didn't realize. Thanks.
So,
Go ahead, Ali.
thank you, Rob. So my name is Ali. I'm part of Dr. Song's research group. My main research focus is on the dynamics of the wind turbine drivetrain. So the main goal is modeling, having a dynamic model for the drivetrain of the wind turbines, in order that we can see the effects of each fault in each components of the drivetrain, and see how the vibrations transmit from the faulty parts to the other parts. So the main components of the drivetrain are in our study in general are the gearbox, bearings, and couplings and brake. So our focus is on the faults of these components. For example, we have modeled the local faults such as cracks in the ball inner rays and outer rays of the bearings, and also the waviness and its effects on the vibration of the drivetrain, which is actually a kind of distributed kind of a fault in bearings. The other type of faults that we have simulated in the drivetrain is the faults in the gears, such as the local faults like cracks in the teeth, and the manufacturing errors, especially the random manufacturing errors caused in the process of manufacturing. And also in the couplings, if the coupling is not completely rigid, if they are loose, there's a chance that the stick slip happens in the coupling. So we have modeled this phenomena in the drive line of wind turbines, and also the other that can also happen in the brakes. So in the next step, we are working on the coupling of the aerodynamic forces with this drivetrain and its effect on the vibrations of the system, and see how the coupling between these faults and these faults can change the vibrations of the system. So it was a whole idea of our research. So thank you very much.
Thanks very much. Okay, so next we have a friend of mine. Hi, Majid.
Hi, Dr. Kariwa. How are you?
Oh, I'm great. I'm really happy that you're presenting. This is a proud moment for me. Majid used to be my student, and we're really excited that he got to work with our good friends at Weekend. So take it away, Majid.
Thank you, Dr. Kariwa. So my name is Majid Morshedizadeh. I'm the Reliability Research Engineer here at Weekend. In this brief presentation, I'm going to talk about our activities or overall activities related to our wind turbines drivetrains. To start with, I want to just explain that we do have a unique drivetrain, and in contrast to what you just saw in previous slide, basically we have a two-stage gearbox, in contrast with more conventional three-stage gearboxes, which is coupled with a basically equipment called wind drive. Our gearbox basically brings the speed of rotor from 16.3 to around 465 at rated production. And then we'll couple to wind drive, which will bring the speed to 1800, constant 1800 for our synchronous generator. Our wind drive has basically it's a two component, two basic components. One like a gear set that acts like a third stage of a gearbox, and there's this hydraulic component with the help of the application of guide vanes. Basically, it provides the constant speed for the generator. We have had our share of failures, or maybe more than fair share of failures in our drivetrain components, mostly in the gearbox. We have had failures in the bearings. The axial cracking was the major problem we've had. We have also had some issues with gear tooth. As you can see, like in this picture, a very clean, beautiful cut in one gear tooth. And we have also had some issues with generator bearings. So we do have a condition monitoring system installed on all our 5 turbines, and we basically collect vibration data and all particle data from our turbines. We have basically installed 5 3-axial accelerometers, one on main bearing, 2 on the gearbox, 1 on the planetary stage of the gearbox, 1 on the basically higher speed stage of the gearbox, and 2 accelerometers on each side of the generator. So we collect high frequency raw vibration data, and we basically do a lot of different analysis with these data, from extracting statistical measures from the time series to frequency domain analysis, something like simple FFT, or more complex wavelet or amplitude demodulation, Cepstrom, or empirical mode decomposition analysis. For example, this picture that you can see in the middle on the right, there's sort of the first mode of one decomposed signal of basically failure data, and on the basically below that basically in that photo you can clearly see the impacts of the failure. This is for a bearing failure, and then on the basically below graph, the amplitude demodulation of the signal that points to the inner race fault frequency of the turbine that we saw. We also collect all particle counts, as I said. You can see on the bottom right picture. And it is also really important to know about the operation condition of the turbine when dealing with vibration data. This is what, as Robbie pointed out, we collect operation and weather data, and we try to do correlation analysis. For future, we are basically we're advancing our system to increase data quality and quantity. Especially for vibration, we are not collecting enough data in terms of both sampling frequency and duration. We're basically talking about a few seconds of data. So we're improving that very significantly. We will be able to collect simultaneous vibration data from multiple points and do a better correlation analysis and understand the normal operation and the effects of special or transition events. Thank you. Back to you, Dr. Caribou.
Thank you, Majid. Much appreciated. Okay, so next slide, please. Okay, fantastic. So we have a presentation from Dr. Mashopoulos from Western University. Mashopoulos, sorry. Thank you. Hi, Jerry. How are you?
Okay, I'm fine.
Great. Please take it away.
Okay, thank you very much. And first of all, let me thank the Canadian Wind Energy Research Network for allowing us to present our work on the comprehensive model for the study of the electrical, mechanical, and aerodynamic aspects of wind turbine systems. Now, next slide, please. Okay, so about 10 years ago, this model for wind energy systems was developed at Western University. The lead researcher on this development was Dr. Ruhollah Ahmadinejad, who was a PhD student at the time, now a professor at Kerman University of Advanced Technology in Iran, and he was co-supervised by me. Now, what makes the model comprehensive is that it considers the electrical, mechanical, and aerodynamic aspects of wind energy systems and the interactions between all three aspects rather than just one aspect. So in other words, instead of focusing only on the electrical or only on mechanical vibrations, what we're trying to do is trying to look at the interactions of all three. Now, this model was developed by using dedicated software, then feeding the output generated by one software package to others and vice versa. And this is where I'll focus on mostly on this presentation. So next slide, please. Okay, so what we're showing here, this diagram is a typical wind energy system. You have wind blowing on a turbine, and you have a gearbox, and you have interaction with electrical. And eventually, the idea is that this energy goes to the grid. Okay, so what we have is we have different software packages. So we have, for example, TurbSim, which is used to simulate three-dimensional turbulent wind. FAST is used to simulate the mechanical aspects of a wind turbine. Aerodyne is used to simulate aerodynamic forces. And the Simulink is used to model the generator, controllers, and power systems. And the idea now is that we have these various components and to make them work all together. Now, some of the programs I mentioned, the TurbSim, Aerodyne, and FAST, have been developed at the National Renewable Energy Laboratory in the US, and they are available to the public. Next slide, please. Okay, so TurbSim, just to go a bit more details. TurbSim is a stochastic full-field turbulent wind simulator. It uses a statistical model to generate a time series of three-component wind speed for Aerodyne-based codes. Okay, now you also have the Aerodyne, which uses blade element momentum theory. And what that does is it passes its results to FAST. Now, the effects of blade deflection and velocities on blade aerodynamic forces are accounted for in Aerodyne. And for this Aerodyne, you have some pre-processor software, foil check, airfoil prep, etc. It can be used to create the input files for the aerodynamic tables in Aerodyne. So the idea now is, okay, that's fine. So the idea is that you have information with these softwares, and I'll show you just very quickly what the interaction is, but let's continue. Okay, so you have now blade and tower mechanics considered in the model. For example, you can take a blade, you can divide it into 15 parts, and for each part, look at pitch, twist, angle, chord length. You can define these things, and then you can do a comprehensive analysis of a flexible structure using FAST. FAST does modal analysis, and modal analysis is kind of sort of like a finite element analysis, but it's mostly for vibrations. So you have this FAST, and with this FAST, this can simulate 2 or 3 bladed wind turbines with numerous degrees of freedom, such as yaw, angle, tower bending modes. And in the diagram, it just shows some of the things that you can look at with this FAST. Okay, next slide, please. Next slide. Okay, so now here I would say is the important point of this presentation, and that is the interactions of the various softwares. Okay, so you have Aerodyne, you have FAST, you have MATLAB Simulink, and what this slide shows is kind of like these interactions. So with FAST, you can define certain parameters, let's say related to furling or the blades, and then you have the Aerodyne, the aerodynamics, and Aerodyne can get inputs from TurbSim. All right, so that's the left diagram. The right diagram shows the interaction between the FAST, the mechanical dynamics of the induction machine and wind turbine, and the Simulink, okay, which is basically the electrical aspects of the wind energy system. Next slide, please. Okay, so this would be the overall wind turbine control structure, and this is interaction of mechanical and electrical once the aerodynamic and the wind aspects have been dealt with. So then what you can do now is you can design your controllers to try to make the system operate as best it can. Okay, next slide, please. Okay, so I mentioned to you that we developed a model. This is part of Dr. Fadnajad's research work when he was a PhD student a number of years ago. And since then, we've worked on a number of projects. So the model has been used to simulate a wind turbine with doubly fed induction generator, to study the impact of tower shadow, yaw air, and wind shears on power quality in a wind diesel system, assist in the investigation of horizontal and vertical wind shear effects on wind turbines using a wind turbine emulator, study the impact of voltage sag, study flicker effects, study how StatComs can be used to mitigate voltage fluctuations, investigate the use of flow control, et cetera, et cetera. Okay, next slide, please. Next slide. Okay, so just to conclude here, okay, so the work that has been done has been mostly simulation work. We have a wind turbine emulator has been developed at Cornell University, but can only look at certain phenomena. Now, what we're interested in is more experimental confirmation of the model, but getting data from manufacturers industry has proven to be very, very difficult. So what we're really interested in is collaborating with interested parties, companies, academia, research institutes, to help us achieve the goal to see about the model. I mean, certainly, it's based on software that has been proven, but nonetheless, it would be nice to have experimental replication. Okay, so that concludes the presentation, and I just mentioned the bottom, the first paper where the model is introduced, in case anyone is interested, and I thank you very much.
Thank you, Jerry. That's tremendous. I believe that takes us to the end of our presentations today. So I would now ask, I guess I will invite, and I'm not sure, and forgive me, I will defer to the weekend boardroom because maybe I missed this memo, but was there a particular format you wanted to follow for the discussion, or I'm happy to try to lead/stimulate some discussion unless there was something specific you wanted us to cover.
I think it can be a combination. If people have questions they want to talk about, that's fine. But I think it would be great if we could talk about, maybe what we see as some gaps in the industry and some barriers to some of this research.
Sure. Okay. Yeah, I scratched that down. So maybe to be fair, because I feel like I've talked a lot already, does anyone have questions for anyone else? Maybe we've got some non-speakers who've been in the audience who wish to have ask a question to one of our speakers. We'll give some time for that.
Hello, Rob. This is Mehtat from University of Waterloo. I had a question, very general, and I wanted to know if there is any guideline on when we say a turbine is reaching the end of useful life. What are the criteria for this kind of specification? That, for example, we are getting there, and then we are using different methods to extend the life, but when is the time that we think, or what are the things that points to that point in time that this is the end of life?
Okay, that's a fantastic question. Does anyone want to offer I can put something together respond to that, because it's a great question. But I don't know if anyone among our panel or in the audience wants to speak to that question before I say anything. Charles?
I can have a first try. I've been attending this end of life seminar, which is held by Wind Europe over the last 2 years. You may know that in Europe, they have older wind farms. And so they've handled the question of wind farms reaching end of life before us, at least on this side of the pond. And right now, there aren't really standardized guidelines. There are some entities looking into this. So Lord Registers, for example, and UL are working on streamlining end of life assessment. But we cannot say right now that there's an international standard on this. So there's like general industry good practice, but there's no specific standard.
Yeah, and it's such a difficult thing to put a pin in, because different owners may have different definitions of when that asset no longer is useful for them. So that but I do know, like Charles pointed out, there are some bodies working on guidelines, but your question is an excellent one that is frankly saddling a lot of the people that are doing research in this area.
Thank you very much. And one more thing is that we know that there are many components in the wind energy conversion system, and they may reach end of life at different points in time. I mean, it may not be the same time. And you were talking, and your colleagues have been talking about repowering. It means that for example, bring something to change one part or one component and give it an extra life. So it's not that all of the turbine system will reach end of life at the same time, I mean, all of the components. So we can let it survive for a longer time by changing or improving one part, one component, I think.
That's correct. That's true. And I'll just quickly respond, and then if anyone else wants to add to it, the real trick is understanding which ones are most important to change, and then particularly if you've got some that are very difficult or costly to change or exchange, what other ones can you change while you're doing that to save money? Like, let's say that you needed a crane to change a main bearing or something. Well, you need to say, well, geez, what other ones can we change while that crane is here, etc. So yeah, it's a really interesting optimization challenge for people. Your observations are very well informed.
Thank you.
Okay, do we have any other audience questions?
I have a question, comment to the group in general. I noticed that most of the work that is being presented and it's been discussed and makes sense, I guess, to me, it's mostly focused on DFIGs, where you have different mechanical parts, different characteristics that somewhat are similar from one machine to another, one wind turbine to another. So I wonder, how about these more recent technologies, permanent magnet type of technologies, have less mechanical systems? What is the experience of the audience or the people in this type of asset management? Because it has less parts, more electrical, do they last longer? Are there any studies on that?
Good question, Claudio. Does anyone want to handle that?
If you look at the offshore turbine development, you'll see a big move towards the direct drive and fewer gearbox stages. So I think that's evidence of experience in that industry, where reliability and that serviceability piece, can you go out on site and what wind conditions, wave conditions? So the reliability piece, I think, has driven that.
Yeah, good point, Curran.
I had a question. I was interested, the partners and pieces. One, piece I'd be interested in hearing about more there is obviously the turbine OEMs that'll sell you maintenance packages, and they have their big SCADA systems back to headquarters. It sounds like you're working more with the actual owners. I'm just interested, are they buying packages from those OEMs? Are those expiring after 5 years and then they're doing their own thing? Kind of how does that play out here in Canada?
I'd like to offer my own experience just because that was one of the most important parts of our research beyond all the sort of the techniques in the analytics, was managing those relationships. And our experience was that we had owners that were, I would say, uncharacteristically very interested in the health and comprehension of the physics of their assets. So some of these owners had packages and they still wanted to be involved. And historically, we've dealt with a number of different owners, and the one thing they've all had in common is they want to know as much as they possibly can. And so where they could, I found they would try to put OEMs over a barrel to say, please make us as informed as we possibly can be, and we'll be better partners for you. And that in our case, that's what it was. And that's how we got access to the data that we did. Because like you said, it is tempting. And some owners, it's more attractive just to set it and forget it and pay for a comprehensive package. That was our experience. Other people may want to chime in.
Did you have issues then with data sensitivity from the OEMs? Like, is it their sensors? Is it the owner's sensors and those data streams, or they have access to whatever they want as owners? Or
yeah, so I don't want to put any of our partners that are here today on the spot. So I'll just say that what I always understood was that, you know, we always had great clearance because most of these owners had really good relationships, extensive relationships with the OEMs. So they knew what could be shared and what couldn't, and we would never go beyond that. And typically we had our hands full with what that was. Even, you know, the one part that only ever got touchy in the early days would have been, you know, trying to mess around with the blades, but a lot of the sort of the bigger scale, more robust things that were less sensitive to maybe graduate students crawling around inside, you know, that information was pretty available.
Just maybe to add on that, Rope, from our experience, and Robbie's slide, I think, hit on this on what took a few years to work through with our OEM to gain access to better granularity with the data. You really have to rely on a good relationship there. You have to be very open with what it is you intend to do with that data and why it's outside of your service agreement with the OEM. So I think everyone's going to be a little different, the purpose and effort that you're working towards as well. Speaking to some owner operators and especially owner operators who've got a business in other industries as well, I think traditionally, at least in the early years, we were, as an industry, at least in Canada, probably a little more reliant and long-term thinking on long-term service and OEM contracts, whereas some of our peers in oil and gas, for instance, it was a desire to get purchasing shorter service agreements and warranties and learning about your infrastructure over those original years and then taking it over and managing cost yourself. So I think every wind farm's a little different, every OEM's a little different, but at the end of the day, most owner operators that we've spoken to try to get more than the standard offer as they get more and more comfortable with managing your own system.
Scott, this is Tom. Just picking up a little bit from that. We back ourselves into a corner then in that regard. We put too much reliance on OEMs, and now owner operators don't have a good sense, or at least I guess it's growing, of what that data can do for them to help inform some of these questions that Rup and his colleagues are trying to answer. Do the owner operators in a general sense have access to that data more so today than they did a few years ago?
Well, it's kind of what Rup mentioned though as well, is be careful what you wish for, because I mean, we're unique. We're similar to what Nergica mentioned. I mean, we've got researchers around and we've got people around who live for this type of data. And it can be overwhelming. I mean, as we add these additional points, and you saw from Robbie's slide, I mean, we basically quadrupled to tenfold increases in our data, and you can drown yourself in that as well. And turbines are extremely complex. I think all the slides show that, and component to component. There's a lot of interaction there that has to be well understood through the drivetrain with outside variables that have to be well understood as well, and experiences. And on top of that, every platform's a little different as well. So when you've got uniqueness of those various drivetrains, you have to be extremely careful, jumping to conclusions on what the data might be telling you. So it's expensive to get the data, it's expensive to hold and manage the data, and it's expensive to hire the people that you need to bring solid conclusions and actions from that data. So in a lot of cases, I would assume the owner operators make a decision. Do you trust your OEM and pay them to do it? Or do you invest yourself? Or do you find a hybrid somewhere in between? And I think more and more we're seeing hybrids, just like most hybrids, some take on a little more than others, right?
Yeah.
Thanks. Yeah, I mean, that's a keystone question to this process because it's so data dependent. And as I mentioned, it's not just the other piece, and I emphasize this at the beginning and I'll reemphasize it now. Having data handed over to you and then people walk away I didn't find was of much use to us because it raised way more questions than it ever answered. And so you need data and you need support with the data that's handed to you. And that was a key piece for any success that we had. That was all on our partners who provided us the support along with their data, to look at their data in its raw state, to look at their data after it was analyzed, to point out our mistakes. And so that was super key. And that's a really important part, is developing your relationships with your partners in addition to, and they have to understand what the value is for them. And that was a painful learning process for me because, and our team, because we really wanted to provide value all the time, and trying to communicate what was value. People have different definitions of what value is, right? So certain people, people aren't always really excited about a journal paper, and I can understand that. And so you've got to be able to provide all those different value points. And I know most people on this call understand that, but certainly was an education for me, and it's something to think about. I wanted to ask a more general question maybe of the audience, and that is, I don't know, when I was looking at Claudio's slide, the first one that came after my stuff, Claudio, you had a nice results. I forget, you'd reached some threshold of success there, about 86% or something. I can't recall. But my question.
No, maybe I clarify that briefly. It was 83% for
83%. So my question is, was it obvious to you or in your team, to go, if you wanted to improve that, was it obvious to you what it would take to improve that? Did you need different data, more data, or more time calibrating the technique? What if you had more resources available, would that necessarily improve your outcome?
Well, that's a good question. I guess one of the challenges we had is the amount of data was not enough in our case. So we consider the success relatively good given the data we had. We believe that if we had more data, we might have been better, more successful. However, having said that, even with the data we had, we struggle, especially with some of these algorithms, tuning them was really challenging. So you start picking things and you have so many parameters. So at the end of the day, that's where we sort of settled in this ADA boost, which required very little tuning and it still created very good, successful results.
Yeah.
So I think that would have been sort of, if we had more data, that's the way we would move forward and see how that works. But then be careful with our, we gotta be aware that we were just looking at failures, right? So it could have been electrical, could have been mechanical, could have been anything. The only differentiation we had, because we had a lot of data, voltage, current, 23, 24 signals that we got in the data for each one of these machines. And then we tried to figure out from there the failure, right? And yes, whether it was on service or whether it was, maintenance and all of that information. But at the end of the day, we are only doing a very simple analysis saying, is it operational or not, right? And we only look at 1 hour ahead. That's another thing you gotta be careful here. Because we're only looking 1 hour ahead, we can be more accurate. When we try to look at 12 hours, the success rate went down significantly, right? It was more difficult to predict. So all of these parameters play a role, right?
Very good. Thank you. Does anyone else want to report on maybe what they thought, you know, if they could ask the powers that be, either people that are here or people that we don't know yet or we haven't met yet, what do you think is missing to take your techniques or your success rates higher? Does anyone want to offer something that they considered was a barrier for them that maybe would be something we can put in the lap of a Phil McKay, for instance, who rallies this at the national level, right, and put this on part of his agenda. So, I mean, so let me ask this then, Phil. Can you comment on, you know, you've been on many sides of this, and you know, your role continues to evolve, but what do you think from an O&M standpoint is, you know, sort of what do you think needs to happen next for this type of, I mean, it's this started as sort of a, hey, we should start looking at this, you know, let's say 5-7 years ago, and people started working on it, and now it's become its defined sort of own space, which is great. But, you know, for us to get to the point where it's truly operational, it's not sort of like teams descending in and let's do an analysis or let's do a 2-year study, where it's truly baked into an organization, or it's baked into the OEM's designs. What do you think has to happen next so that happens?
Yeah, it's so big, Rup. It's I think I was at least happy to hear a lot of the discussion about relationships and power purchase agreements and getting I mean, there's that technical side of it that takes folks like those who are on the line to really develop these complex models to understand what you can actually change. But it runs its course all the way through the industry. So I don't have a good answer for that one. I maybe have a few thoughts I could throw on the table that might get some others thinking. But I mean, the one piece that I was thinking, I can't remember who was talking, but if actually you said it up front, when you go in and you ask for everything, you ask for all the data, it's a pretty daunting thing. And so if you've got an owner operator who just expended some relational collateral with the OEM to say, hey, I need a lower price on this because this is not going to work. Now I also want all the data. That's challenging. So if there was a go-between, I don't know if we can, or somebody wanted to say, specify the data set that you want. And then maybe in an industry forum, we could put out, okay, somebody's looking for this specific driveline data to run a model against. And so it's got the parameters around it. It's got the outcomes decided. I don't know. It's a lot of upfront work on the research side to actually define all those things. But then the owner of that data knows what's being asked of and might be able to quantify what the response is. Just a kick at the can here as I'm thinking on the fly. I think there are some initiatives that are starting to indicate next level. So as we talk about all these uniqueness aspects, the relationships between somebody who bought the machine and somebody who sold the machine, there are groups out there like the Enter Alliance, ENTR Alliance, who are working on open sourced SCADA standardization for wind energy. And so that to me indicates, I don't know if that's the winner here, but indicates to me that, okay, Vestas, Siemens Gamesa, Enercon, here's the standard SCADA tag, which eliminates a lot of that really difficult, confusing work on the research side when you're handed a data set that has that, like you said, generates more questions than answers. So there's that piece of it too, as we harmonize and try to standardize some of this information. There's, I think, the added layer of challenge here. So we've just talked about these machines, but now we're integrating those into the grid, which introduce a whole other suite of data points. So I don't know, it's so big. I don't have a good answer. I have some ideas.
It is, and no, you raised good points. Your last comments about integration was something when I saw Tom pop up. The role of wind is continuing to be pushed to be more dynamic, and some of that is wind pushing itself, and some of that is people asking more of wind, which I think it rightfully should. And so I guess here's a question for Tom. Scott's involved in this work too, I know, but does anything change with the life expectancy of a wind farm when you ask it to do the things that it's being asked to do now in terms of providing different services? Does this modify the way we perceive, O&M for wind?
I know Scott's got some views on that. I do as well. I won't comment about how quickly we killed the battery at weekend before, but that might be for other reasons. I think there's been some discussion, and actually when Power Advisory was doing the Nova Scotia PPA work, they were looking at how to modify that. There's a public report out on that, and we hands down on record as saying, look, there's a lot of questions that have to be answered around the provision of these services. We might be putting extra strains on different components of the turbine. Inverters might get a little hotter because we're bouncing them around faster and asking them to move quicker. And so I think, some companies will say there's no impact. Other companies will say we don't know. And then other companies might say, yeah, there certainly is an impact. I think it boils down to there probably isn't enough data out there. Even in established markets like Ireland, where they've got now, I think, 14 different services that different synchronous and non-synchronous generators can bid into, I don't think they have enough data out there to really answer that. My gut feeling is, sure, you're bouncing something around more, you're going to cause extra strain, you're going to move it through its paces and move it outside of maybe where it was even rated to operate. And then notwithstanding that, the IEC 61400 measurements that are always around maximum production at any rated wind speed or rated capacity, we're not testing under the conditions that we're asking these generators to start operating within. So yeah, I think the answer is yes, but I don't think we have enough data.
Yeah.
I'd just add, Rupp, I agree with everything Tom said. The one thing I'd add is money talks. I mean, when you repower, I think it was Claudio asked earlier, and when you make that decision, a lot of that depends on what you can do with that property that you're on. Rupp's slide started with that and all of the considerations, land-based PPA, etc. Right now, I would suggest repowering for some of these sites looks pretty lucrative because you can get access to capital for record low interest rates. If something changes in 3-4 years, that money becomes a lot more expensive. It's probably going to have owner operators trying to eke out existence with existing assets. I had the same conversation earlier today with someone on the solar side who needed to make an investment in an installation that was only 9 years old. But with where the cost of that infrastructure has come in the last decade, it was a pretty interesting discussion, purely looking at numbers. So coupled in on that, you mentioned the services that wind farms can or are now and perhaps soon will be called upon to provide more of. What's the market going to be? Is it going to be you have to do this or you don't gain access to the lines, or is it going to be can you provide it for the following fee? And then each asset and each OEM platform is going to look a little different as well. It's kind of early days in that. I mean, the other thing that's really starting to change, especially in the provision of auxiliary service, and Tom sent me an article on the side this morning out of Australia that showed some incredible things going on down there with relatively small installation of storage, offsetting immense traditional generation provision of frequency support, inertia, etc. So as those demonstration projects get out there a bit more and markets and system operators get more comfortable with utilizing them and deploying them, I think we're going to see a lot of really unique things going on, and we're going to have to be ready to react.
I also want to, like, you know, the interesting thing that's coming into my mind is we're assuming that the grid services and the volume of those services that are going to be procured is not going to change. And so one of the things we've looked at is, well, what's the size of the operating reserve market in Ontario? And it's pretty small. It's only like, it's less than 500 megawatts. But as we keep displacing synchronous generation and as we keep digitizing our loads more and more, is that market going to grow or is it going to shrink? And or the size, the volume of these reserves, what's going to happen to that? So, you know, I think there's a lot of unknowns that are out there, and that becomes a difficult thing to predict if you're trying to figure out, well, where is the market? Where does it need to move to? What's the volume of different non-synchronous generation that I need to hold back to provide secondary frequency response? Or, you know, how much inertia can I get from my batteries? How much do I need for the system to hold it all together? There's a lot of questions that are at the utility level that I don't think they even know how to grapple with, because I don't think our models are sufficiently able to represent that future system yet.
I may comment on that last comment from Tom. It's interesting because we're working with the ISO precisely on this, trying to figure out, they don't know that. So they're trying to figure out what would be the size of that market, what kind of resources they would need, they want to increase it, how, what kind of impact batteries would have on that, or other energy storage. So they are actually looking at these questions actively, in particular the ISO. Other jurisdictions have already addressed some of these issues. PJM, for example, they are quite advanced on this. Australia is looking at these issues in level of, which was already mentioned, I guess. So I guess depends on where you are, but yeah, but that's an interesting question. Some utilities are more advanced than others and know better what they need, and some others are trying to figure it out. Yeah.
Thanks, Claudio. I'm getting a message here that it's time for a wrap. And I want to say I appreciate everyone's participation, our presenters, our audience members, our wonderful hosts at WeCan. So thanks for that. I'm instructed to inform you that the recording of the webinar will be made available shortly. And the next one will be Wednesday at 1:30 Atlantic time. And if you have feedback on this webinar, please reach out to Marianne Rogers at WeCan, who you've been in communication with your feedback. So thank you very much, everyone. And please enjoy your week. I look forward to speaking with all of you again soon. Take care.
Have a good day.
Bye
Thanks,
now.
Rob.
Thank you, Rob.
Thanks, all.
Thank you, everyone.
Bye-bye.
Bye.